So today we're going to go over kind of a quick tutorial on zeros. So just something I wanted to note. Zeros are the x values, such as when you solve for x. And whenever you solve for x, remember you always set y equal to 0. Graphically, that makes them the x-intercepts. So given the zeros, -2, 1, and 5 of a function, they're asking for the expanded form. So you're actually working backwards from solving, meaning they're telling you the zeros or what x equals to. X equals -2, x equals 1, and x equals 5. So they're telling you the values of x, which if you were to graph them, not that you have to, they would be points on the x-axis. Anytime you're solving for the values of x, you're setting y to 0. And notice any point on the x-axis, the y value is going to be 0 for that coordinate. So they're all interchangeable. Okay, so continuing on from here, we're working backwards. So if I know x equals to 2, that means in the parentheses, it would say x plus 2. Because if I set x plus 2 equal to 0, it would give me x equals -2. My next parentheses, if x equals to 1, would say x minus 1. And last, this would say x minus 5. So remember that we set them equal to 0. We change f of x or y to 0. And that's how we solve it. And we got x equals -2, x equals to 1, x equals to 5. But we're going backwards here. So we're actually trying to find the original polynomial, meaning you're going to expand this by foiling and using distributive methods. So I always pick the first two. Mind you, it's multiplication, so the order doesn't matter. But I usually like to pick the last two to foil. X times x would give me x squared. Outer, x times -5 would be -5x. Inner, x times -1 is -1x. And last would be -1 times -5, so that's +5. And usually when you FOIL, the two in the middle are like terms, and they are, so -5x minus 1x would give me -6x. Everything else comes right down. The x squared, the +5, and the x plus 2. So since the second parentheses has 3 terms, you are no longer going to, I'm just going to move this down, I need more room. Since the last parentheses has 3 terms, you can no longer apply foiling. You have to use what's called distributive method. So following up on distributive method, that means I'm going to take x and multiply it by everything in the second parentheses. Then I'm going to take the plus 2 and also multiply it by everything in the second parentheses. Okay, so let's get started. We're going to distribute. Remember, this is x to the first power. Anytime you don't see an exponent with x, it's technically x to the first power. So x to the first power times x to the second power would give me x to the third power. When I multiply like bases, I add their exponents. X times -6x would give me -6x squared. X times 5 would be 5x. And then distribute the 2. 2 times x squared would be 2x squared. 2 times -6x would be -12x. And 2 times 5 would be 10. And finally, from here, you're combining like terms. So x to the third power has no like terms because nothing else has x to the third power. We have -6x squared plus 2x squared, which would give me -4x squared. And then from here we have +5x minus 12x, which would give me -7x. And finally bring down the plus 10. And this is the expanded form of the function. So it means you're pretty much just working backwards. They're giving you x this time, and you are going to give the original function that it was beforehand. So then last up with the zeros. So given the zero of a function f of x, x equals 10 minus 7i. So they're already telling you the zero again. Rather than working, backwards all the way to get to the original polynomial, they're just asking, what is the other zero going to be? So one thing to know about when your answer is a complex number, meaning real and imaginary, they always travel in what's called conjugates. Complex numbers travel in what's called conjugates. Conjugates have the same terms, but they have the opposite operation. So meaning, if I have 10 minus 7i as a zero, then the other one would automatically be 10 plus 7i. So you're not changing the signs of the terms, just the operation itself. And this actually stems from once upon a time you had your quadratic formula. I'm just going to take a sidebar here. Remember, your quadratic formula was x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And sometimes in this square root it was a negative, which made it an imaginary number. And it's plus and minus. So there's the plus and there's the minus. So that's where it stems from. So anytime you have a complex number, it will have a conjugate automatically as the other zero. All right, guys, I hope this helps.